Alright, draft physics video. Do a little lensing first, and then Mindless wants more info on the relationship between magnetism and electricity. And it's a good subject because I haven't finished it yet, so it's a place for lots of thinking. So we'll do some of that. So I'll play some of this Hothloday response video. So the gist of his first argument is this distance argument. You know, if you go far enough away, then the angle gets smaller and smaller. So yes, if my hand is here and I have to get to this little point here, then that's a really steep angle. But if I move this thing further and further away, the lever gets less and less and less and less. So at 5 billion years, it's a little tiny angle. I'm still going to argue that by those same distance rules, the distance between galaxies is monstrous. The distance between suns inside of galaxies is monstrous. So you're talking about diluting something like the sun like by 1,000,000 times. You know, just making it lighter and lighter and lighter and lighter and lighter and lighter. And I'm arguing that that lightness is happening at least the same rate as your angle diminishment. So as your angle is decreasing, the amount of fluff in your matter is increasing by some sort of proportional amount, let's say, for the sake of argument. The other arguments are mostly about this idea of a focus, and the primary argument I'm making, so we'll go to the image of one of these lensing things, and it's really irritating because these images suck, and then when you go to the full resolution, it still has their stupid graphic in it. They can't even show you the undistorted image. They have to keep showing you distortions. So that's as big as it gets. I'll move up here. So, you know, yes, it's obviously they have, you know, extracted everything they can out of this because everything's, you know, fuzzy. But what is this? I wonder what they think that is. Anyway, so this is the thing. This is one of these lens things. So they say this is 3 different images. Well, I don't even know how that happens. And they say this cluster, I guess, is what's causing the gravity. Now, I just can't tell you how there's just so much empty space in here. It's an incredible amount of empty space. It's not dense matter. And so the gravity's got to be, you know, minuscule. More importantly, my argument is if you're lensing this well out here, look how well that's lensed. I mean, that's just a beautiful image, right? And why is it only just this arc? Where's the rest of it? Why doesn't the rest of it happen? So you have to ask questions like that. There has to be a reason, because there's no obvious obstruction. There's no obvious reason for the gravity to poop out. So why isn't it, if it can make 3, why can't it make 4 or 5 or 10 or 12 or 15 or 100 images? Like I said, I can't figure out the logic of this double image crap anyway. It just doesn't make any sense at all to me. From the same location. But the more important thing is okay, so with computer enhancement, they turn it into this stuff. And so we're supposed to believe that this galaxy is about proportional, to tell you the truth, to the other galaxies. You could sort of imagine that maybe it's the average size galaxy. So this one's 5 billion, this cluster's 5 billion light years away, this one's 10. So this one is behind here, and it's showing up over here multiple times. See, the trick is that the light from that could be theoretically actually parallel. You know, like the lines are actual parallel lines to the place that it's ending up because of the size proportion. So this is at a size proportion, but you know, the distance doesn't change the actual size of things. So I mean, here's the eyeball. This is the only place that the angle has to be an angle. So going to the 5 billion years, you automatically have this angle. And then what you do with this, you know, this distance you can vary based on how thick your lens is. But my point is this this whole part of the lens. So this whole part of the lens can actually see further out angularly. It sees a bigger circumference. It sees a bigger circle of the universe. So the very outside of the lens can only see a little tiny piece of the universe, but the strong part of the lens can see a bigger circle. So it's a lot more of the space. So lensing theoretically by just probability should be really sharp around heavy gravity. There should be lots of lensing happening. Well, where is it? I mean, this cluster is crowded. There's lots of stuff here. So we're supposed to believe that back 10 billion years ago, right? 10 billion years ago, when the universe was supposed to be a much smaller universe, right? Supposed to be smaller. So a more crowded universe. And we can't see anything else in that lens. That's why I'm saying it can't be lensing. Because then everything would be lensing the fuck out of everything. There would be, like, we'd look at the universe and we'd see like 10 universes. Because everything would be lensing, and they'd be lensing the lensing. Right? This is 5 billion light years away. Why don't we try to lens the lensing? It doesn't make any sense. Alright, but the real point is look at the detail here, and then just realize that, you know, maybe they made the little round stars with the computer. That was probably just a big cheat. But just the fact that there tends to be something, the idea of spherical is definitely in there. So, but I don't know how enhanced this image was. It's actually two different images superimposed on each other. You know, they're black and white images that they colorize. You know, the whole thing is, you know, who knows what the original shit looked like. But regardless, let's say this has some sort of theoretical integrity and this image has something to do with reality. The argument I'd also make is this is hugely thick. So, and it's even thick here. I mean, you're talking about, you know, by their own, they had a scale on the other picture, but the scale would be, this is like 5,000 light years. You know, one inch and a half or so. It's 5,000. So this is like 60,000 light years across, 70,000, something like that. So you're saying that this has got to be at least 10,000 light years across, maybe 20. And so how can the inverse square law produce this quality of image? Just by chance? It just turns out that the inverse square lens, which is a huge fisheye lens, right? I mean, the gravity here is, you know, a million times stronger than the gravity here. You know, huge fisheye lens, and it just happens that it can the non-parallel angles that this is traveling to here, right? I mean, if they were parallel, you're dead in the water, because parallel would mean, you know, that huge giant swath doesn't have any change in the gravity. It would have to be all the same gravity through this whole thickness for these to be parallel lines from the source. So they can't be parallel. But how can they not be parallel because of the size? How can it be the correct size, proportional to the rest of the nebulae, the bits, the galaxies in the cluster? How can it be proportional in size to them if the rays weren't parallel from the source? And then the inverse square law would make it impossible for that to happen. I'm just saying this is just so, you know, there aren't just such, you know, this is like quantum mechanics. This is a double slit all over again. It's just all these, it just doesn't make any sense. It's not so much that you can't contrive an excuse for something. You can't explain all the things that implicates if it were true. Again, how do you get the copies of the image? That doesn't make any sense. Realistically, you know, they're different angles. This one's going this way. This one's going this way. How can the same galaxy produce two things going different directions? They should be wildly distorted. If you could do it at all, which I'm saying you can't. And if you did this much of the arc, theoretically you should have the whole Einstein ring, technically, because to do this much of the arc in the same gravity requires the rest of the galaxy to also be centered. So it has to be exactly behind this. Just about. It just doesn't make any sense. Alright, is there anything else I got to say on that subject? So it's about the fact that if you're going to argue this is lensing, then how do you explain that in all this heavier gravity, nothing's getting lensed when its reach is much further? Its arc of influence, the stuff it can focus on, is much bigger. So something theoretically, even something outside, something we could actually view, you know, with straight on, without it being obscured by the little secret object, you know, theoretically could be lensed by the lens, and we could see it over here and over here. The real image here, and we'll see a ghost of it over there. I mean, that's what you can do with the thicker glass, so to speak. So this doesn't make any sense. Let's see, what else do I have to say? Well, that's probably enough. I'm just saying, yes, you didn't fully understand the argument. My argument is, why is the lensing always so far away from the gravity? When, as Einstein said, it should be right next to the strongest gravity. It's where you have the highest probability. And you have a very lower, weaker probability the further away you get from strong gravity. And you people are saying somehow exactly the opposite. Somehow there's a reason that, yes, it's always far away. Why? Alright, it's probably enough on that subject. Well, no, I was going to play some of his crappy video. Still haven't finished it. So I haven't played all this, so I don't know what's coming, but we'll play this part because I don't know what's coming next minute.
About the dimensions in which gravity operates. It doesn't even operate into it. It gets in all three dimensions, and the inverse square laws working on all three of them and diminishing the inverse square law and affecting by the inverse square.
Alright, so he didn't even understand the argument. He's saying it's in all three dimensions. It's not in all three dimensions that the light from, say a light bulb. The light's coming at me, so that has nothing to do with any dimensionality. It's heading right for me. Okay, so that's not the part we're talking about. We're talking about the spread of the photons. So as the photons go further and further away from the light bulb, they go further and further away from each other. So it's like the balloon expanding. I pump air into the balloon, and I put dots on the surface of the balloon. The dots go further and further away as I blow the balloon up. Well, that's exactly what happens in gravity, and that's exactly what happens in a light bulb. That's the inverse square law. So the point is the dots are moving away from each other this way and this way in those two dimensions. Obviously, they're moving this way. That's the relationship. It doesn't have anything to do with the third dimension. Is irrelevant to the spread of the photons that are all released at the same time. All the photons that are released at the same time are doing this thing. They're spreading. And the point is you're just cutting one little path through that spread. So yes, you might be able to keep up with some of the spread this way, but the spread this way is wiping you out. It's taking you right out of the game. That's what it means. Sorry you can't understand that.
Fuck the inverse square law. That's Newton's science. He's rejecting Newton in every way.
No.
He's just saying fuck the inverse square law.
No, you need to pay attention to the inverse square law. That's the problem. It's a law. It doesn't go, oh.
Yeah, it's a law, right. So that's an argument. You're just going to say it's a law, when I'm the one saying, yes, I'm the one defending it. You're the Looney Tunes saying, let's go far, far away, because if we just make something far enough away, it doesn't matter. We can lens you know, at preposterous distances. So let's just, if we take the sun and move it further away, we can lens. So why don't we look at Alpha Centauri or something, and why don't we lens with it, since we'll be able to lens much further away because it's, you know, hundreds of light years away. Well, whatever, 5, 10, 15 light years away. So yes, obviously the light will be in the gravity much longer. So, you know, we go 3 radiuses away from that sun. Oh, but no problem. We should be able to lens the fuck out of shit. So why don't you do that? You know, I was even thinking of Jupiter. I mean, you know, Jupiter is surprising. You know, it has pretty good gravity. Okay, it's 2.5 times greater than the Earth's gravity. So it's like 25 meters per second. And the sun's only 80. So it's a pretty close, right? So if you take away the sun's corona, you know, if you concede that you can't do any serious lensing in the sun's corona because you can't tell it from scatter, you know, then you'll get, so you get a radius away from the sun. Well, you're knocked it down to 20. So I mean, Jupiter's got 25. Now Jupiter's much smaller, so you're not in it as long. So that's a downside. But the plus side is the angle is smaller because Jupiter's smaller, so the amount of distance you have to bend it, right? I mean, obviously the bigger something is. What the hell is in my kitchen? It's not monstrously huge. Alright, so from the same distance, you could sort of see that if I put a dot the same distance and dot this same distance, this angle is much smaller, you know, that I have to bend the light, theoretically, right? And Jupiter's much further away than the sun. It's like 4, let's see, how much, 4 times the distance of the Earth. I mean, the Earth to Jupiter is like 4 times more further away than the Earth to the sun, I think. Something like that. I think, okay, that one I'm not sure of. So you have 2 advantages. You have first advantage, the Jupiter's further away. Second advantage, it's smaller, so you don't have to bend the light as much because it's not as big a arc. So that's a win. So you got 2 advantages with Jupiter, and almost the same gravity, because you can do it right on the surface of Jupiter, because you got no corona problem. So you got a huge advantage there. So yeah, why don't you do this lensing shit with Jupiter? Because theoretically it's pretty close. I think the numbers will come out pretty close to what the sun's capable of doing. Tell me I'm wrong. Go ahead. Show me I'm wrong.
Oh, nah, I'm not going all out there. I'm not going all the way out there. I'll be worth nothing out there. Let it go by. Let that photon, yeah, you can come around the outskirts of me. There's only 200,000 solar masses in there, yeah, and I'll get to that in shortly. But
yeah, 200,000 solar masses separated by 1 billion solar volumes of empty space. So for every solar mass, there's what, 1 million, 5 million, 10 million solar volumes of empty space. So the solar mass is diluted by a huge volume of empty space.
Go by, don't worry about us. I'm only dealing with things that come close to me. I'm not a law. You know, I don't enforce the law over there. Just around here.
So again, I mean, you know, light bulbs are kind of deceptive because nobody puts their eye right up next to a light bulb. But the amount of light you're getting, say at a mile away, that's almost what they're talking about. Is put a light bulb on and walk a mile away and see how much light you get. I mean, it's we can't appreciate the actual circumstance, so we can't see it as just light bulbs. But you can sort of see it when you look in the sky. I mean, the tiny stars, the tiny amount of light they are actually producing that are getting to your eye. It's a tiny, 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 tiny fraction of what the actual thing has produced. And distance is what made it that tiny fraction, because with all the distance, all the little photons are getting further and further and further apart. They're getting further and further and further apart.
He seems to think that his description of why he doesn't buy lensing images, he's called that a mathematical argument. I pointed out to you that Einstein's math doesn't make it possible, so you...
This is another. You don't know Maxwell's, and you don't know Einstein's math.
Okay, well, what's your point? Where did Einstein say, yeah, go ahead, go look at a sun, because he knew suns existed. I think he knew galaxies existed, but let's just say he didn't know galaxies existed. And he just knew there was suns out there, a ton of suns. Where did Einstein say, go look at any old sun out there, because it's far away, and then you can see something further away, okay, anywhere around there. All you need to do is find the right combination of sun and the other sun being the right distance away, and then just maneuver yourself until you get the two of them behind each other, and bingo. No problem. No, he didn't say it was no problem. He says it's a big problem. And he says if you're ever going to see an Einstein ring, it's going to be right the fuck next to the sun. It's not going to be, 10 radiuses away.
Right? Because I don't know Einstein's math, but I have a better feel for it than you do. Right?
It says you, arrogant, pompous fuckhead.
The video.
I mean, apparently you don't understand the spreading argument in 2 dimensions. You don't understand the galaxy argument. Pi versus this way. You don't get that.
On it. Yeah? I've never seen you write an Einstein equation. I have. Right? And I've talked about parts of it.
Who cares? I'm just saying, what I do understand is what the relationships are to the things in there. The distance argument. I know what that R squared thing means. Gnarly, gnarly. It means whatever you're measuring is either getting extremely weak very fast or it's getting extremely strong very fast. But that's what it means. It means a fisheye lens.
I understand the genesis of it and the story that backs it up and how it's only recently you started accepting it's about geometry, not force.
I'm not accepting any of this shit, so I don't know where you're getting this crap from. I don't accept your silly geometry argument. I mock it. It's a non-explanation. Oh, we have an equation that recognizes the inverse square law. We're going to call that geometry and say that makes the universe work. Well, that's the silliest motherfucking pile of shit I ever heard. How do you get away with that crap? The geometry did it. Oh, you mean the law did it. Oh, okay, but there's no mechanism causing that. Oh, that's physics. No mechanism. Yes, that's what just create a bunch of invisible men. I just keep calling them that, but that's all it is. Accepted anything. I've accepted that you people are retarded. And so I'll sit there and I'll use your own words back at you. Well, the geometry did it. When I say that, I'm being sarcastic. Newsflash.
Right.
You shouldn't be putting Einstein's name on it.
Look, and that's the other book, though. This is an argument about whether light can bend, first and foremost. Not whether it's Einstein rings, or whether it's Einstein crosses, or whether it's whether Einstein said in 1920. I don't think we'll see it.
Yeah, whatever. Yeah, you haven't proven light can bend. That's the whole point. Because none of this shit, okay, can get over the contradictions it creates. As soon as you say it's there, but we can't see it. Why can't we see it? Again, if you're going to say this lens exists, where's the consequences of it? This is stronger gravity. This is stronger gravity. This is stronger gravity. This is stronger gravity. There's nothing in the rest of the universe. The whole arc behind that thing doesn't have anything else in it that's on fire. Nothing. That whole hunk of the universe is dead and it only has this one fucking thing in it. Bullshit. If it wasn't every single lensing image looks exactly like that. Every single time it's so fucking far from the thing that's supposed to have the gravity that it doesn't make any sense, because the laws of averages are, no, you're going to be more likely to have lensing in the strong gravity because it creates a wider hunk of the universe that it can potentially lens. Shit. Stupid
It's
bastard.
possible. You know, the people now understand this theory better than he did. Maths wasn't his.
Okay, see, so here we go. Yeah, fine. I'm just saying that it's pretty silly to put a man's name on something like dark matter and the rest of this crap. I think it's rude as hell, because I know Einstein debated these subjects and he wouldn't want his name put on it in the way you're creating it. Like I said, this isn't anything to do with Einstein's perception of what lensing was possible.
Strong point. It took him 10 years practically to get to the bottom of that. And, you know, he had to have mathematicians holding his hand most of the way. Grossman, you know, half of the maths isn't named after him. You know, Lorentz contraction. What's it called? This is the space, and that's the.
Yeah, well, all that stuff was done before him anyway, so exactly. Why should it be named after him? He just incorporated a bunch of the existing things that we already knew about. Again, the movie The Time Machine, right? The script, the book was written before Einstein was even born.
This is the spaces. But the space-time vector space isn't named after him. You know, the solutions to his equation, you know, the hypothesized black holes and everything, he found very few multiple solutions to his equations himself. So it cannot be about an argument about whether sort of slandering Einstein. And
yeah, I think it can be. I'm just saying that every time they put Einstein's name on something, I'm just saying that where did he say the things you're saying are what he thought were possible? And I'm just saying he didn't think you could put a billion hunks of empty space in the sun and expect it to be able to lens. Let's make it 1 billion times lighter. And yes, it'll be bigger, but it'll be 1 billion times lighter. And we're going to go do some serious lensing with it. And not just 1 radian away, radius. No, let's do it 10 or 20 or 30 radiuses away. Whatever, enough of this crap. Alright, so let's do some electricity shit. This argument is, you know, we had it, like I said, 1.5 years ago or whatever, and I guess it was a draw or some kind of silly thing. But again, the arguments haven't been addressed in terms of all the things that if that's true, lots of other things should be true. So if this happens, multiple images, big, hard, nice line. The question is, why isn't there other shit being lensed here? Because you have apparently a strong enough field of gravity, even though this field of gravity is 1 million times too weak. You know, let's just ignore that because of the distance. It's just, yeah, sorry, it's a bullshit argument. All right. So I'll do some electricity and then call it an evening. So I don't know if I want to. I guess I won't. I'll address the specific things in your comment. I guess mindless. But first, it's just getting to the theory part of it. So let's understand. Okay, so we know there's a relationship between magnetism and electricity. But what we also know is that you can figure out anywhere, deduce that some things, like electricity flying through gases and stuff, doesn't create much magnetism. So you can run quite a bit of electricity through like a fluorescent tube, and I don't think you create much of a magnetic field. So obviously certain conductors don't create the same amount of magnetic effect. And so you can sort of see that aluminum pipe versus copper pipe versus steel pipe, and then you drop a magnet in and, you know, it'll fall at very different rates. So it's more about the conductor than it is the electricity, let's say. So there's two, I guess what I'm trying to say is there's two effects. The first effect is being magnetized, and the other effect is when electricity moves through a conductor, it magnetizes the conductor. So there's two things. So when you apply a magnetic field, you can make the conductor capable of transmitting current, facilitate it, let's say. Probably not even the right word to say. Alright, well look, it's all this monopole argument. So if you think in terms of, as one of the arguments, that protons and electrons are really magnetic monopoles. And so even though people think of them as being, think of electrons as being associated with electricity, they're only associated with electricity in the sense that they allow the force of magnetism to move through something as a current, and we call that electricity. I think that's a way of saying it. Alright, this electromotive force. Electromotive force. Yes, I think that's what they call it. I always thought the EMF was electromagnetic force, but whatever. Electromotive force is what electricity is. Alright, so what I was thinking was, this is about the stupid arrangement of the atoms again. So the basic theory is that if you have a bunch of, let's see, how can I draw these so it's understood that, well, I'll just do it this way, and then I'll put red heads on them, and then we can understand what's being said. So theoretically, atoms can be in different arrangements, so that would be the domain argument. And when they're in different alignments, you could sort of understand that they're not going to be doing any consistent filtering. So there won't be any magnetism. It's only when they line up with each other, you know, red, black, red, black, red, black, red, black, red, black, kind of a thing. And then, you know, the staggering idea where the red and the blacks, oops, I did it backwards, didn't I? Yes, I did. So black, and then red, and then black, and red. Alright. And, you know, this is the construction of a magnet. So in a conductor, what you're essentially doing is constructing a magnet. Now, somehow, when you force electricity through, you end up creating magnetism. And how much magnetism will be related to the current, but I think it's also related to the conductor you're using. So depending on what conductor you use, you'll get more magnetism out. Not certain of that, but I think so. So what I'm thinking is happening, this is my current, could change, that electrons really aren't doing any moving. They're just doing this stupid jiggling thing. You know, they're switching their positions. So let's say that the electron end is pointed out, and well, let's suppose the electron's a little ball, because that makes it simpler. And so the line is just the association to the proton, let's say. And so when you bring a magnet into this circumstance, I guess what I would argue is happening is, you know, at this end here, these electrons are getting pushed this way. You know, pushed down. Right? Right. And these electrons are getting pulled up. Alright. Yeah, that works. And so the protons are likewise changing their position. So as the electrons push down here, the protons swing this way, and vice versa here. Protons are getting attracted to the red end, repulsed, so they're going back to the furthest away position. So, those aren't exactly perfectly done. So it ends up that you start creating the same kind of magnetism that's here. So they're starting to polarize all these things into one direction, into a you know, a red and then black at the other end. So they're lining up by being pushed into each other. So they're starting to get in the same direction. If you get my drift. And why that facilitates the flow of electricity, yeah, so then we have to get the protons back into the game. So, alright, so when you push the electrons down, you're pushing them into other electrons, so you're increasing the amount of force between them, so they don't like it. You're pushing them into an unnatural position. And so there's more pressure on the electrons interior to the electron you push. So if you're pushing an electron from here to here, that electron is going to push this other electron, and that's going to push, say, something else. But the point is the element that is capable of creating the current is the proton, in the sense that the magnet is filtered for these little black bits that are the things sensitive to electrons. It's hard to draw this stuff. So this is the quanta, and this is the stuff hitting the let's say it hits the proton. Well, when it comes in and hits the proton, it does that perpendicular thing, right? And so that perpendicular thing means it's creating more pressure on the electrons, so they're getting squeezed even more. So you can almost argue that in this process, you're squeezing the electrons, creating more pressure, that would also make them tend to bulge. So that's the backward, the reciprocal magnetism, essentially. So where do I want to go with that, though? Oh, yes, but it bounces back and then comes back out of the protons. So the force goes in and comes back out again. And even if it goes in this way, it's just sort of inevitable that it's going to end up coming back out again. So that's one way to explain the magnetism being like it's fighting is the word they use. So they always say that it fights the magnetic field. So when you induce a magnetic field, it has exactly the same north-south relationship, which means it's repulsive. So the field you create is a hostile magnetic field, not an attractive one. It's a repulsive one. Correct. So where do I want to go with that? Yeah, so that's the part I haven't. You have to understand that the electron and the proton are doing that, that right turn thing. So, the black stuff goes into the proton and it goes out perpendicularly. Now the question is, there's these four directions, and how that ends up interpreting through the whole course of this thing into a reciprocal more reflection. Now the other part of it, though, is that is it just a reflected magnetic field, or is the arrangement of the matter such that it creates the magnetic field? So when the current's going through, it's creating a legitimate magnetic field. So let's deal with that part. So there's a wire, and you have a current going through it this way. So let's say those are the black quanta, is the real energy behind that current. And so that means you're creating more pressure on the electrons. And I guess what I'm arguing is that requires them to separate more, and because of that greater pressure, or it obligates them to stagger. So they push out of alignment. And that has the reciprocal effect on the protons. So then you end up with an alignment of the electrons and the protons when the current's going through the wire. And that's creating your magnetic field. So somehow it has to create, it's lining up the domains. So the current somehow creates a pressure. Well, we know it's pressure, it's voltage. So it's a higher pressure. The higher pressure gets transmitted through the electrons. The electrons move in some way. And in that being forced to move in some way means the protons have to compensate for that movement. So I guess what I'm arguing is this, it's just sort of this, if there are all different kinds of lines, the current basically straightens all the lines and, you know, creates your monopoles, creates your magnetic alignment. So the current doesn't allow the atoms to be in their natural state. So they're in this magnetized state. Now, question is, all right. I was just trying to think of electromagnets, but they always use a coil that magnetizes some other conductor, some other hunk of metal, you know, like when you wrap a wire around a nail. And yeah, the nail can become magnetized, but the coil of wire doesn't stay magnetized. So clearly in the conductor, even if you use steel wire, the steel wire probably doesn't become magnetized. But I'm not sure of that one. You know, which ones hold the magnetism. So clearly copper doesn't hold any, and aluminum and those things. So their natural state is for the domains to be scattered, which might just mean that in their natural state is always temperature sensitive. So that's why superconductors work, is because it's temperature that's causing the domains to be out of alignment. So it's the vibrating, you know, moving of this stuff. And so when there's a current, it can't vibrate. Everything gets rigid, let's say. And so it stays where it is, but it's only staying where it is because the flow of the electron force, the black stuff, is steady and is forcing the domains to stay lined. Now the question would be, it also creates more magnetism the more voltage you put through. So the more current, the more magnetism. So that would imply that it goes deeper and deeper into the conductor. The more current you're putting through, you're affecting more and more of the atoms in the conductor and forcing more and more of them to line up consistent with the flow. So again, that would almost be like say if you had a river. Okay, maybe that's the way to think of it. You had a river and you put a compass needle in it. You know, which way is it going to line up? You know, and it's kind of not a seriously asked question. You know, north, red, black. Well, obviously if there's a current, a flow of stream water coming through here, it's going to line up so the stream water creates the least resistance, so it's going to line up with the water. Yeah. And so maybe it's that simple. Something like that. So I have to find a parallel for that argument, that the electron-proton relationship, as the electrons are transmitting more force between them, that something about that causes them to spread. Well, that's what I said before. Yeah, so it might be. Let's see if this is a way I can draw that. Alright, so here you have 2 protons and 2 electrons. Now if I force more stuff between these 2 electrons, so there's more pressure, what they're going to tend to do is move further away from each other this way. but this one would tend to go this way, right? If they were moving away from each other, and that wouldn't work. So they've both got to be pushed the same way, so they both got to go this way. But that would sort of be the idea, is that they both go this way, and that means that you end up with the potential to create magnetism, because you're aligning the protons and the electrons. Something like that. Yeah, I have to think on that one some more. So anyway, it is complicated. I did write a few notes, so I'm going to finish up here, so I'm getting tired. So yeah, this whole jiggling thing is important. So how much they're vibrating. So that would also be a giveaway to how much they release quanta between them, pressure. So if there's two electrons, and they're jiggling in a random way. This one going, so this one's going this way, and this one's going this way, with a little bit of jiggle. Well, the stuff between them could quite easily escape. So anyone that was like right close to this place here, when this one jiggled this way, it would leave, and then this thing could swing back, but it let one of the force elements loose. So jiggling can allow the force elements, it can relieve the pressure, because the stuff is moving around, its position is inconsistent, so it's doing this kind of thing, and the stuff going back and forth isn't trapped, because it keeps getting released every time it jiggles in an uneven way. But if you can force them to jiggle even, then you can maintain the force between them. So that might be something to do with this too. Alright, so let's see. Electron force released through the proton. Yeah, that's just that's sort of the, that's where it gets complicated. Because like I said, that certainly would give you your perpendicular reflection. So it sort of makes sense that the force hits the proton, the black quanta, goes perpendicular, reflects off an electron, comes back in, and goes out perpendicular. So that would be a reflection. So I have to think of reflection as a way of describing what magnetism is really doing when it creates a magnetic field in a conductor. That the magnetic field in the conductor is just a reflection of the magnetic field that's hitting it. And it doesn't have much to do with the flow of the electricity. It just has to do with the fact that you're, through that reflecting process, you're going to end up losing some force, and you lose the force perpendicular to the force that created the magnetism. So yeah, that's a good one. So the paper. So the magnetism. Okay, so I know colors do help though. All right, so there's your magnet. So the magnetism goes in, and then it hits the proton, and it leaves perpendicularly, bounces back, and let's say it reflects out this way. Alright, through that process, what's happening is the electrons, because you're increasing the force, the electrons have more pressure, and they, let's see, if they jiggle unevenly, no, that really won't, so we have to explain where, okay, so that explains the reflexive magnetic field. And now I have to explain why that also creates a current in the wire. So as it changes. So it's only on the change part. So obviously when this higher pressure is created, the electrons move because they can't deal with the higher pressure. So they move to a new location. When they move to their new location, they release the field energy between them. So yeah, so there's two electrons here, let's say. So when this one reflects, So the force comes into the proton, goes this way, hits an electron. There's another electron that's associated with that one, okay, and that's got a repulsive force. And so now this one has more pressure, so this one feels that pressure. They end up going uneven, like one goes this way and one goes this way, or whatever happens, and then an extra black bit is created, okay, that leaves this way or whatever, and they can hit another electron downstream. So I have to explain why it always goes in one direction, though. Why does the current move in one direction? Alright, so that one I'll have to work on. Well, it moves in the direction that the magnet's moving, so that sort of makes sense. So, yeah. So, as the magnet's moved, it's inciting protons, it's creating more force. So I have to explain why it's creating, why it's always a right turn, let's say. It always goes in one direction. So that'll be the part to explain. It ends up in one direction. Like I said, it can go through a bunch of the conductor before it gets to this process. And this is, I'm just giving a surface example. But this process would feed into the rest of the conductor. Alright, that's worth thinking about. Alright, yes, that's probably enough. Yeah, so it's about movement, but not movement like going somewhere. It's about moving relative to the proton. And the fact that under pressure, there's less chance of vibrations or jiggles from heat. So adding pressure takes away the ability for the little stuff to bounce around. I have to come up with a metaphor for that. Yeah. This pressure will do that, right? Pressure makes it harder for something to bounce around. Greater pressure. Alright, anyway, I'm tired. So, till next time, I'll work on it some more. So anyway, I guess the answer to your question is just, yeah, I'm not done yet. I'm just saying that the basic idea that this polarizing thing is obviously what the mechanism is. It's, in my opinion, it's just kind of obvious. And figuring out the exact chemical model, and that's sort of what you're asking, is for the chemical model. Yeah, I haven't got all that yet. But, you know, the theory is, you know, it's there. It's just you got to work through the permutations and find the one that doesn't, unlike their lensing argument, the one that doesn't create a bunch of unanswered questions. So anyway, I think that's all for this edition of I Hate People. But anyway, till next time, such.